Hey guys, we're Farmer back with part two of doing equilibrium calculations. I'm actually going to get into a couple of example problems with acid-base titration. The two examples I'm going to do in this video are a strong acid with a strong base, and we're going to do a weak acid with a strong base. And I'm going to use exactly the same um, volumes and concentrations, and I want to look at the difference between those two. A quick little review here for you guys. If we're doing a weak acid and a weak a weak acid and a strong base, this is the curve that we're going to get. If I'm going to do a strong acid and a strong base, this is not the curve I'm going to get. I'm going to get a curve that's going to look something like this. Okay? So this isn't going to have a buffering region. What is going to control a strong acid, strong base? It's simply stoichiometry. The only equilibrium we're looking at is that of the autoprotolysis of water. It's the equilibrium, the Kw equilibrium. Okay, so let's look at this sample problem. I'm going to be mixing a strong acid, hydrochloric, with sodium hydroxide, a strong base. The balanced equation for this is hydronium plus hydroxide goes to water. There are no sodium or chloride ions in here because they are spectators. This is the balanced net ionic equation. So if I go into this problem, you are going to need to use moles, right? I'm looking to get the pH, which means I need the hydronium concentration. If we look, I have 50 mils of 0.1 molar HCl, 25 mils of 0.1 molar sodium hydroxide. You are going to have to get moles. Molarity times liters is going to give you moles. So you need to do that to find the moles of your acid and base first, doing the stoichiometry to get to the concentration. We're going to do initial, we're going to do change, we're going to do final. So let's start with the hydrochloric acid. You have 50 milliliters of 0.1 molar. Remember, you're multiplying by liters here. That's 0.05 liters. That's going to give you a mole of 0.005. I'm leaving off the other sig figs for now just to save room. Okay, you should follow through with 3 sig figs on this problem. The hydroxide, there's 25 mils of 0.1 molar, so obviously it's going to be half of that value, which is going to give us, sorry, that's 25, 0.0025 moles. Well, if we're taking a look at this, if I have twice as much acid as I have base, the base is going to be your limiting reagent. So what I'm going to do is I'm going to go into my change. Since this is a limiting reagent, all of it is going to react, right? So there should be no hydroxide ion left at the end. Remember, I'm not worried about water. The hydronium has to go down by that same amount, okay? Because there's a 1-to-1 mole ratio, which means that's going to leave me with 0.0025 moles of my hydronium. Now, I hope you know technically we don't have 0 hydroxide. You know, there's still that equilibrium there that we can calculate, but the problem is not asking for that. We only need to find the hydroxide or the hydronium to get the pH. So this is the moles. This is not the pH, right? This is not our concentration, rather. We need to put this back into concentration to find pH. That's moles over liters. Well, the moles we just found. What are the liters? Whoa, you got to go back up into the problem, okay? Go back up in here. You had 25 mils of base added to 50 mils of water, which gives you a total volume of 0.075 liters. That's 75 milliliters of total solution. So that's really important to take into account, right? We're going to do that problem. That's going to come out to be 0.0333 molar. That's to 3 significant figures. It's, you know, you'll see that it's obviously repeating. And that's going to be the concentration of the H3O+. Okay. Obviously, there isn't 0 hydronium. You could actually go and calculate what that is using the Kw expression. We don't need to do that. We've already found the hydronium. We're going to get the pH. The pH is equal to negative log of the H3O plus So that is negative log of 0.0333. Just looking at that number, I know it's going to be something between 1 and 2, right? It's between 10 to the negative 1, 10 to the negative 2. That gives me 1.477. That's 3 sig figs, right? You need numbers after the decimal place are the only ones that are actually significant in a pH because this is a logarithmic scale. So 1.477 is what we're going to get. If I go to this little graph, my expectation, I'm still going to be down here. As you add base, right, I'm at the half equivalence point, right? If you think about that, let me go back. I'm at the half equivalence point. I've added exactly half as many moles of base as I have acid. If I come back over here, right, where am I? I'm still way down here. The pH of this titration or this reaction would not go up until I get way closer to the equivalence point if I'm using a strong acid and a strong base. Okay, in the next problem, what I'm going to do is take those same numbers, and we're going to do this with a weak acid. Okay, exactly the same calculations, except this time we're going to use a weak acid, and we're going to use our Henderson-Hasselbalch equation to figure this one out. So you'll notice this time I have acetic acid. I'm giving you a Ka value in this one. Not right. We didn't have that in the last one because it wasn't a weak acid. Exactly the same volumes, exactly the same concentrations. Okay. So I'm just going to repeat what we had before. I'm going to put in the same first numbers right here. This was 0.005 moles. This was 0.0025 moles. Notice now I have my conjugate base appearing. So that's important for us, right? That didn't appear in the last one because it was strong. This went down. This is our limiting reagent still. Right? Notice changing to a weak acid doesn't affect the mole part at all. Right? It affects what we're going to get for pH, but not the mole part. So doing our stoichiometry, this one's going to go up by 0.0025. Each of these will go down by 0.0025. So that's going to leave me with 0.0025, 0 hydroxide, and 0.0025 of my conjugate base. Now, I can go and find these molarities, right? I can do moles over liters if I want to, 0.0025. What was our total volume? Same as it was in the last one, 0.075, which is going to give us that same concentration, 0.0333. But that's going to be the same concentration of our conjugate base and our weak acid. They're both going to be the same thing because I have the same number of moles and the same volume. Well, where are we? We're at the half equivalence point. We're going to be up here. What do we know at the half equivalence point? HA equals A minus concentration. So if we go back, take a look. When we go to do the Henderson-Hasselbalch equation in this one, pH equals pKa plus the log of the A minus over the HA. Well, because these two are the same value, like we said earlier, if I put 0.0333 in for both, that's going to give me 1, which means the value of the log of 1 is 0. So my pKa is equal to the pH, or the pH is equal to the pKa. So my answer is going to be to take the negative log of whatever I was given up here. We almost didn't have to do this part if you could realize that we were at the half equivalence point. So, I'm sorry, let me go to I was on the wrong one. The pH equals our pKa plus the log of A minus over HA. So our pH will be the negative log of our Ka value. Go back up into the problem. It's 1.75 times 10 to the negative fifth, right? Take the negative log of that, you're going to wind up with 4.757. 4.757. I know that it's going to be something between 4 and 5 because we have a number that's between 10 to the negative 4 and 10 to the negative 5. Okay, so that's where we're at. pH equals pKa at that point. And I'll come back in the next one and we'll look at when we're not at that. Okay, so we just looked at a strong acid and a strong base. I'll be back to look at ones using Henderson-Hasselbalch for a weak acid at some other point in the titration.